Hi, everyone. Welcome to the second and final lecture bite for this week in Astronomy 236. This week, we're talking about the Big Bang theory versus steady-state cosmology, which was an alternative theory that was popular in the 1940s and 1950s. So usually we have 3 lecture bites per week, but this week we have just 2 longer ones because that's how the topics seemed to organize themselves the best when I was preparing this. So last time I talked about how Hubble showed us that galaxies appear to move away from us faster the farther they are from us. So on this famous Hubble diagram, on the y-axis, Hubble is plotting the velocity that is measured of these galaxies. And on the x-axis, he's plotting how far away they are from us. And he found 2 very surprising things. The first of these is that almost all of these galaxies seem to be moving away from us. Only a handful seem to be moving towards us. The other thing that he noticed, which is perhaps the most important part, is that the further away you are, the higher velocities you get. So these galaxies over on the right-hand side that are far away from us are moving faster away from us than the closer by ones are. So what does this mean for the state of the universe? What does it mean that you have galaxies that are nearby, that are not moving much with respect to us, but when they get further away, they start moving away from us faster? Now, I want to remind you that in the 1910s and 1920s, people believed that the universe was relatively static. And this kind of makes sense. We don't see changes to the universe on our human timescales. Why should the universe have ever been created or ever been destroyed? Shouldn't it always just kind of be there and not really changing very much? And this was the state of what we thought the universe was. We talked about this in the Great Debate lecture last week. You can count the stars in the different directions of sky, and you can see that we seem to be in this flat, disk-like structure of stars, which we call the Milky Way. And we learned last week that eventually we were able to figure out that there are these other island universes that are very similar to the Milky Way, called galaxies that are out in space. But it was believed that these objects, these stars, and these other galaxies were not really moving with respect to each other all in one preferential direction. We knew that stars moved with respect to others in the night sky. We knew that galaxies were moving because we could measure their velocities using Doppler shifts. But we didn't really know whether or not, or we didn't really believe that any of them moved coherently. We didn't believe that any of them moved all in the same direction. But that's what Hubble showed us. And this directly contradicts this idea of a static universe. So how do you fix this? How does your model of the universe have to change to take into account Hubble's measurements, and also to take into account the fact that general relativity predicts that there should not be static solutions to the universe? One solution is to imagine that the density of the universe is decreasing. So how much matter you tuck into the same area is decreasing over time. So imagine you start off with galaxies that are distributed like this. They're not all on top of each other. This is maybe what we see today, but they are far apart in some cases. When you play forward these velocities, and imagine that all of these objects are expanding away from each other, what you'll find is that this seems to match Hubble's observations. The galaxies that are close to each other only have to travel a short distance, so their velocities with respect to each other are pretty small, which is what Hubble found. The closer by galaxies are not moving very fast away from us. So I'll show you this again. Keep an eye on this galaxy that's right next to the purple galaxy, which we assume to be our Milky Way, which is going to stay stationary, the closest one to the left here. And keep an eye on where it moves and how quickly it gets there. It's moving much slower than these others that started off a little bit further away. And that's just the consequence of how this expansion is taking place. Everything's getting puffed up as if it's on the surface of the balloon. So what does this imply if this is actually how our universe works? Let's take this state that we're in right now and let's run the clock back. So as we go backwards in time, everything's going to come back to one point, and we're going to have a lot of matter all stuck together very close. So when you run back time, you think you realize everything must have started off with a very high density. Now, I want to make it clear that while I'm showing all of the galaxies right on top of each other in one place here, that's not necessarily how it has to be. We could have lots of matter spread out everywhere that just happens to have a high density. That's what the theory actually says. So this idea that everything is in a single point is not necessarily what we're saying here. But what you'll know is that if you have everything come together, if you bring stuff close together, and you take gas in particular and bring it together and make its density very high, gas will heat up. So what this fellow is doing here is he has air in a syringe, and he has some cotton fibers in that syringe as well. And he's taking a plunger and he's hitting it with his hand, and he's compressing the air in that syringe. And what that does is it increases the density of the air and therefore increases the temperature. And it increases the temperature so much, in fact, that you can actually ignite the cotton and cause the flash. So this is something that would also happen if all of the matter in our universe were compressed to a high density as well. It would be very, very hot. So, so now that we've run the clock back all the way to the very beginning at very, very high density, let's run it forward again. And you can imagine now that you have everything starting off very hot and then it's expanding and cooling off. And this is why we call this model the hot Big Bang, because it started off all hot and clumped together, and then it went bang, everything started moving apart, and we get the universe that we observe today with the velocities of the galaxies the way we observe them too. Now, I want to note that in this model, the velocities that we see for these galaxies are not necessarily due to the normal Doppler effect. If you solve the equations of general relativity, what you find is that we're not necessarily saying that the galaxies are moving away or are moving. What we're saying is that space is expanding. And when that happens, the distances between galaxies get larger, but also the wavelength of light that they emit gets larger. So if you imagine that a photon of light was emitted from one of these galaxies and it traveled to reach us on Earth, then it started off smaller because it was emitted when the universe was younger. And then it expanded as the universe expanded and caused it to have a longer wavelength and therefore a redder color, which we interpret as a shift due to velocity. So another solution is that instead of having a start and a finish to the universe, is that the universe is continuously moving and is continuously expanding outwards, but more stuff is being created constantly to replenish it as it does that. So in this model, you might have galaxies that are moving apart from the Milky Way. And as they get far enough apart, more galaxies form because new matter is being created. This is called the steady state theory, the steady state cosmology, in which the universe is kind of always doing this. The universe has gone on forever. It's been going forever. It will go forever. And the only reason we see everything moving apart is because everything is constantly moving apart and more matter is being created in the middle to create those new galaxies. So these were the two competing ideas in the 1940s and the 1950s about what was the way to explain Hubble's observations of the universe and to reconcile them with Einstein's theory. You have the Big Bang on the one hand, which states that the universe began as a hot, dense fluid, a lot of gas all close together that rapidly expanded, went bang, and cooled, creating the galaxies, stars, and planets that we see today. The other idea, the steady state cosmology, says that the universe has existed forever and continuously produces new matter, new galaxies, which appear to expand outwards constantly. So I'm going to go through some of the arguments that were in favor of each of these two theories and talk about eventually how it was resolved. And I'm going to start out by giving some of the evidence in favor of the steady state. And the first piece of evidence that I'm going to give is actually a really big point in favor of steady state and a really big problem for the Big Bang model. So the argument goes like this. Let's imagine that the Big Bang is true. When did it happen? If we take Hubble's observations at face value, and we believe Hubble when he says that galaxies that are about 2 million parsecs away from us are moving away from us at 1,000 kilometers per second, how long must they have been traveling at that speed? If we wind the clock back and imagine these velocities have been traveling about that fast, these galaxies have been traveling about that fast since the Big Bang, we can calculate when the Big Bang was just by using the formula for speed, distance, and time. So let's do that. And if you plug in the numbers, you find out that these galaxies potentially only need to have been traveling for about 2 billion years to reach the distance that they're at the speed that they're traveling. Presumably, this is when the Big Bang happened, because when those galaxies and the Earth were on top of each other, that's when everything would have been very, very dense. And that's when we would have started the countdown. But this is a bad thing, because scientists at this time already knew that the Earth was older than 2 billion years. They had found rocks, geologic evidence that the Earth was at least 3 billion years old at this time. They had found these rocks and they had dated them using radioactive dating techniques, kind of like radiocarbon dating that you hear about today. And eventually, geologists figured out that the Earth is actually 4.5 billion years old. So in this argument, it seems like the Earth has to be older than the age of the universe, which doesn't make sense for the Big Bang model. So this is actually a big point instead in the favor of the steady state model, because you don't have to worry about this. The steady state model says that the universe is infinitely old and has been doing the same thing forever and will continue doing the same thing forever. So we don't have to worry about the Earth being old enough to fit in our version of the universe. The other major arguments for the steady state model are a little bit more philosophical in nature. It's simple and it avoids some pesky questions. So here's what I mean by that. If you think about the Big Bang model, what you're saying is that everything must have come close together or started off close together and then went bang and started off. But that asks some really important questions. Why did it go bang? What happened before it went bang? Was there nothing? Was there another universe? Why did the universe start when it started? Why has it only been 2 billion years since the universe began? The steady state model circumvents all of these questions because it's far simpler conceptually to think about the universe having always been there and always will be there. We just happened to come along when we came along. So while perhaps this is not necessarily scientific proof, this was a good reason for the people who believed this model to hope that it was right, because it would answer a lot of the questions or circumvent a lot of the questions that would come about from the Big Bang model. So that's the argument for steady state. I'm now going to talk about the arguments for the Big Bang model as to why it's more appropriate than the steady state model. And the first one has to do with the changing characteristics of our universe over time. So what do I mean by that? So what I want you to do is I want you to imagine that you're in a parking lot today and you get in your time machine and you go back in time about 65 million years. What you'll see is that our planet, that parking lot, is very different then. You might see trees, you might see grass, you might see fauna, which are different from the fauna that we see every day in Earth today. And if you went back even further, maybe 4 billion years ago, you would see a very different landscape indeed, because you would still see the Earth being bombarded by lots and lots of rocks from space and causing our crust to be molten. So what you can infer is that over time, the Earth has changed. Now, why is this important? If we're in a steady state, if matter is constantly being produced and new galaxies are constantly being produced, then you should imagine that on average, there should be old galaxies and young galaxies all mixed together in space. And if you look on average at any part of space, if you go back to any time in our universe, then there should be a similar mix of old galaxies and new galaxies because they're being constantly created all throughout the universe. And if that's true, then there shouldn't be big change in characteristics the further back in time we look. So this is all well and good, but it requires us to go back in time and look at the properties of the universe a long time ago. So how do we do that? And the answer is we actually take advantage of a trick. And the idea is that light takes some time for it to travel. So imagine that you have a guy who's firing a laser gun on a car towards a camera, and you measure the light from his laser. What you'll find is that this laser takes some time to travel that distance. If the camera and the laser start off 100 meters apart, then it takes about 300 nanoseconds, 300 billionths of a second, for the light to go from the laser to the camera. So that's not very long, but let's make the distance a little bit larger. Instead, let's think about a star that's about 1 light year away from our telescopes. Now, the distance is very large, it's a light year, and light takes a year for it to travel this distance, by definition. 1 light year is the amount of distance the light takes in a year. So anything we see happening on that star today actually happened a year ago, because that's how long it took for the light to get there. So let's take this idea and let's expand it again. Instead of talking about 1 light year, let's talk about 1 billion light years. Now we have a galaxy that's very, very far away. How long does it take the light to travel from our galaxy to our telescopes? Now it takes 1 billion years. So anything we see on that galaxy today happened 1 billion years ago. And what this means is we can look 1 billion years into the past and look at what this galaxy was like a long time ago. So if you do this for many, many galaxies, what you'll find is that their properties on average change the farther back in time we look. So this graph here is showing a thing we can measure about galaxies, which is how many stars are forming at any given time in that galaxy. And it's averaged over many, many galaxies at many different distances from Earth. So on the top y-axis, you can see that they're giving the look back time. So how long ago the light that we received was actually emitted. And what you'll find is that about 10 billion years ago, 10 gigayears, that's what GYR means, giga is billion, the most stars were being formed in our universe that ever were. After 10 billion years ago, more recently, stars have been forming less often. And before that, stars were forming less often too. This is a clear indication that the further back in time we look, the properties of galaxies change. And it's a big problem for the steady state model, because the steady state model assumes that everything has been going on forever, infinite amount of time. So why would it be the case that if we look back 10 billion years, things were different, if everything's been happening exactly the same for much, much longer than that? The other very strong argument against the steady state model was actually discovered by accident, and this is the cosmic microwave background radiation. So remember from our light lecture, dense, hot objects glow, and they produce light that looks like a black body spectrum. So what else have we been talking about today that's hot and dense? And the answer is the universe itself. The entire universe right after the Big Bang was very hot and very dense. So we should infer that the Big Bang should glow, just like these stove burners are glowing right now. And you'll remember that black body radiation, this glowing radiation from hot, dense objects, has a characteristic shape. And it's this kind of weird stretched bell curve where one side of the bell is longer than the other. And for objects that are hot, so maybe about the same temperature as stars, most of that radiation is released at wavelengths that we can see with our own eyes. So between about 4,000 angstroms and 7,000 or 8,000 angstroms, which is about the same as 400 nanometers to 700 nanometers, so 1/1000th of a meter. Now remember, I said that the wavelength of light expands along with space. So in the Big Bang model, we could imagine that any light that was emitted a long time ago, the wavelength would expand, it would get longer, and everything would become redder. And that's exactly what we see for the cosmic microwave background. The glow from the Big Bang, this black body radiation, has been stretched out so much over time that instead of being optical light, it's radio light. It's in fact in the microwave region of the spectrum. So there's a constant black body light that's bathing us from all directions that was discovered in the 1960s. And this cosmic microwave background is essentially the leftover remnant of the Big Bang. It's the glow, the afterglow from the Big Bang. So summing up all of the arguments, the Big Bang theory predicts that there should be background radiation from the hot, dense stage of the universe, and we've detected that. And there's really no reason in the steady state theory why there should be. That doesn't mean that there couldn't be a reason for it, but it doesn't naturally explain it. The Big Bang model also explains and predicts that the properties of galaxies should evolve over time. Because the universe is young, so we should see changes in the behavior of galaxies the same way that we see changes in the behavior of a person as they grow from being a toddler to a teenager to an adult. On the other hand, the steady state model has philosophical simplicity. It avoids a lot of tricky problems and tricky questions, and it's attractive for that reason. And it still has this ace in the hole that it gives an ageless universe that doesn't conflict with the age of the Earth from geologists. So how do we get around this? What is the explanation for how the Big Bang could be true if the universe has to be younger than the age that we know that our Earth is? And the answer is that Hubble's original relation was wrong. It turns out the distances Hubble had measured using Leavitt's law were incorrect. And the problem was there are actually two different types of Cepheid variable stars, and they each have their own different Leavitt law. Hubble was accidentally confusing these two types of stars, which caused him to measure distances that were smaller than the actual distances. And when he did this, that meant that the slope of his line, the velocities that he measured, were too steep. And it should have taken longer for those galaxies to travel back to the single point than we said earlier, which was 2 billion years. So this plot shows how our measurements of that slope, how our measurements of how fast things are receding according to Hubble has changed over time. The very first observations in the 1920s by Hubble showed that everything was moving away from us very fast. We measure this in a unit that's a weird unit. It's called the Hubble's constant in kilometers per second per megaparsec. And essentially this tells you how fast things are moving away from us. Over time though, astronomers figured out some of the problems with those measurements. They figured out the problem with the Cepheid variable stars, and they figured out problems of other nature as well. Like what happens if there are two stars that are very close to each other that affect the brightness that we measure. If we can correct for that, eventually you get down to a value for Hubble's constant, which is about 70, as opposed to the value of about 500 that he said. So when you plug in these new numbers and you plug in these new distances to the velocities that Hubble measured, you get a universe that's more like 14 billion years old, which is perfectly old enough for the Earth to have come about 4.5 billion years ago. So this solution seemed basically to be the last straw, and figuring this out made it much easier for us to believe that the Big Bang was actually a viable model.